Hi, Mike Collins here for Microlab. In this video I'm going to do a titration of acetic acid with sodium hydroxide using the conductivity sensor, the Model 160 conductivity sensor. I'm also going to be using the drop dispenser and the drop counter along with the thermistor probes in order to monitor the course of the titration. Now, previous to setting up this experiment, I went through and I adjusted the drop size, the drop rate, using the knob on the drop dispenser so that it was a desirable rate, and I also calibrated the drop size. I know that each drop over the course of the titration will be 0.0350 milliliters. Notice here I have the conductivity cell below the surface of the liquid. I've got a stir bar in there. There are no bubbles in the conductivity cell flow cell, and it's all set up and ready to go. So let's start the titration. 5.9.7 is the latest version of the Microlab software at the date of this recording. You should probably check the latest version on the website from Microlab and make sure you have that installed on the computer. We're going to open the default experiment. We'll leave it untitled for now. And what we're going to do first is add the sensors, and then we'll add a formula that relates the drops to the volume of sodium hydroxide. First sensor we'll choose is the conductivity sensor. It's plugged into the conductance jack, and earlier in the previous video I showed how to calibrate the conductivity sensor over the 0 to 20,000 microsiemens range. We'll use that range, and we'll actually read that calibration file from June 26th. There it is, and we'll finish that, and we'll drag that over to the digital display, and we're reading 0 microsiemens per centimeter because right now in the beaker I have deionized water. Let's add the counter. The drop counter is plugged into the counter jack, and I'm going to call that drops. Finish that, and let's put drops in the digital display as well. The last sensor we're going to add is the temperature sensor, and that will be the thermistor, and I've plugged that into Cat5A, and we'll label that thermistor A, and the units will be in Celsius. We're going to read this from a calibration file called the Model 103 thermistor file. This is the factory calibration that comes with the software. All the thermistors are essentially the same. And there we have it. So let's drag and drop the temperature into the spreadsheet. Let's put the conductivity on the y-axis for following the titration. And we're going to add a formula. And the formula will be to convert drops into milliliters by multiplying by 0.0350 milliliters per drop to get milliliters, and that is the volume of sodium hydroxide. I don't know if you can hear that clicking or not. That's the stir. I'm going to adjust it. Okay, and we'll put the volume on the x-axis, and we'll drag that into the spreadsheet. And lastly, for the sensors, we'll drag conductivity into the spreadsheet as well, so we can monitor it as we go. The last thing we want to do is change the experiment from time-based to drops-based. So I just clicked on the repeat every 0.5 seconds read the sensors, and I'm going to double-click on that, and that brings up the dialog box, and I can choose to repeat when the counter changes. It's that simple. So now the experiment is ready to go. Before I start the experiment though, I'm going to add my acetic acid to the beaker. And again, for the purposes of this demonstration, I'm just going to be adding about a milliliter of 1.5 molar acetic acid. No need to be precise in the demonstration. Notice the conductivity went up to about 300 microsiemens per second. The acetic acid is about 0.05 molar after adding it and having it diluted. It's a weak electrolyte, so the conductivity is still quite small. Let's start the experiment. We've got our first reading. Now I'm going to turn on the drop dispenser and start adding sodium hydroxide. There we go. One of the interesting features of weak acids is that in the course of the titration, you're converting the acid form, the molecular acetic acid, into sodium acetate. And yet, early on in the titration, the conductivity actually drops. Now it's going back up. We're converting the molecule, acetic acid, into sodium acetate, which is a strong electrolyte. The original dip is due to the increased pH from adding sodium hydroxide, suppressing the ionization of acetic acid. The hydronium ion has a much greater conductivity per mole than the sodium ion, and so even though we're creating a strong electrolyte, we're actually decreasing momentarily the conductivity by lowering the concentration of hydronium ions. Well, now we're well into the titration and the conductivity is starting up. So I stopped recording while this thing just went on for a while, and now I've started back up again. We've gone through about 360 drops, and you can see a change of slope out around 12 milliliters that indicates that we have actually hit the endpoint. So now we're going beyond the endpoint, adding excess sodium hydroxide. We have an increased rate of change of conductivity because the hydroxide ion has a much greater mobility than the acetate ion, and so the conductivity goes up along with it. We can let this go for just a few more drops and then we'll stop the experiment. I think that's good enough. We'll stop the experiment and I'll turn off the drop dispenser, and there we have it. We've done a titration in which the conductivity started low from a weak electrolyte. Pardon me, it went lower as we suppressed the ionization even further by adding some sodium hydroxide, and then it started back up to the endpoint, and then it went up even faster beyond the endpoint as excess sodium hydroxide was added. Here's our endpoint. You can stop the video now if you'd like, or you can watch while I do a brief analysis to determine the actual endpoint. We're going to select a domain, and we'll just pull this last part before the endpoint, and we will add a curve fit of conductivity versus volume of sodium hydroxide, and we're going to make it a first order fit, and let's call this the pre-line, pre-endpoint. Notice the correlation coefficient at 0.999. It's essentially linear over that brief range. We'll accept and save that. And now we've added a regression line to that portion just before the endpoint. We'll repeat that for the portion beyond the endpoint. So we'll do an analysis, adding a curve fit. Again, conductivity versus sodium hydroxide over the range beyond the endpoint. We'll add a first order fit and call it post endpoint. And now we have a new regression line, post endpoint, and where the two regression lines intersect is the endpoint of the titration. So let's just zoom in on that. And we can see that we have the pre-line, the post line intersecting at 11.98, about 12.02 milliliters. We'll zoom out, and there you have it, a conductivity titration. Thanks for watching.